Okay, we're going to look in this video at the hydrogen ions and how they affect the acidity of the solution and how you calculate the acidity of a solution. So we're going to start by looking at strong and weak acids. The definition of a strong acid is an acid that completely ionizes in solution. A weak acid only partially ionizes. Now, if you think back to the solutions we've been looking at that have ionic compounds in them, they have completely split apart where there is no compound left, there are only ions. Well, that's what it looks like if it's a strong acid, and there aren't very many of those. Most acids are weak acids, where only a few of the little compounds split apart into ions. So let's check out an animation to see what that looks like. Okay, hydrochloric acid is a strong acid. So as the acid is going into the water, you can see down here that hydrochloric acid all bonded together, HCl. As that starts to dissolve, you're going to notice that the hydrogen and chloride ion concentrations go up. The whole HCl concentration goes down until there is nothing but ions left. Okay, that's what happens with a strong acid. All of those ions split apart. They are completely separated. As you can see here, none of the ions are left together. Now, in a weak acid, like hydrofluoric acid, here we go with our HF all whole. Here's our concentration of the whole compound put together. And as it starts to dissolve, you're only going to see one of those little molecules breaking apart. Okay, so we get very few ions and most of the acid is left together as a whole. So you can see here we only get one of each ion and a whole bunch of HFs still put together. So that's the difference between a strong and a weak acid. Now, how does that affect the acidity of the solution? Well, if you have a strong acid that completely ionizes, then the concentration of the acid equals the concentration of the hydrogen ions. Now, when you see something written in brackets like this, it means concentration of, which is molarity. So the molarity of the acid is the same as the hydrogen ion concentration. Now, the strong acids we're going to look out for are hydrochloric acid, nitric acid, and sulfuric acid. There are 4 more, but these are the most common ones. Now, for a weak acid, because that acid doesn't completely ionize, then our acid concentration doesn't equal the hydrogen ion concentration, and that's a concept that we look at more in AP chemistry, how you figure that out. Now, some weak acids you might be familiar with: acetic acid, which is vinegar, carbonic acid, which you find in sodas. So the more hydrogen ions you have, the more acidic the solution is. What about bases? Well, strong bases, just like strong acids, are completely ionized, so the concentration of the base will equal the concentration of the hydroxide ions. Strong acids are going to be mostly alkali metal hydroxides, like sodium hydroxide. Weak bases don't always have hydroxide, but they can still be hydrogen ion acceptors, like NH3, where hydroxide is produced, it just doesn't come directly from the base. So those are weak bases. Okay, so let's get to the calculations. If you don't have your calculator out, you need to get it out because I want you to follow along as we do these calculations. So we're going to look at how to find the pH. Because the concentrations of hydrogen and hydroxide ions are usually very small, they were written in scientific notation. So scientists got really fed up having to write these small numbers out, so a guy named Søren Sørensen came up with the idea of the pH concept. And it's basically just the negative log of the number. And a log, or a logarithm, is a way to express the exponent of 10 that leads to the number. So when a number is in scientific notation, it's just looking at the exponent of 10. In our formula, pH equals negative log of the H plus concentration. Okay? So let's look at some examples. So, okay, here we go. We know that pH equals negative log of the hydrogen ion concentration. So here's our question. Find the pH of a solution if the H plus concentration is 1.0 times 10 to the negative 4th. So we're going to say pH equals negative log 1.0 times 10 to the negative 4th. Okay, now if you have your calculator, here's what you're going to do. You need to find your log button. If it's a graphing calculator, it's probably down here by the 7. If not, you need to figure out where yours is. Okay, so we're going to type in negative log 1.0 e negative 4, just like we wrote in our formula. And the answer is 4. Now, if you'll notice, exponent, answer, they're very related to each other. That's what logs mean, is what is the exponent of 10. So here, our pH equals 4. Okay? All right. Now, our next question says the H plus concentration is 8.3 times 10 to the negative 10. What is the pH? So we have pH equals negative log of 8.3 times 10 to the negative 10. So when you plug that into your calculator, negative log 8.3 EE negative 10, enter, and we get 9.1, okay? So when we look at 9.1 as our pH, we know that's a basic solution. If you remember from middle school, acidic solutions have a pH less than 7, basic solutions have a pH greater than 7, and if the pH is 7, then it's neutral. All right, what if the solution has hydroxide ions? Well, then we use what's called the POH, and that equals the negative log of the hydroxide ion concentration. And then if you know the pH or the POH added together, they equal 14. Okay, so let's do a couple of examples with these. All right, so we said pH equals negative log of the concentration of hydroxide ions, and pH plus POH equals 14. Okay, find the pH of a 0.0015 molar solution of sodium hydroxide. That means the hydroxide ion concentration is 0.0015 molar. So if we know the hydroxide ion concentration, we can find the POH. Okay, so calculator. Negative log 0.0015 equals 2.8. Now remember, that's the POH. We want to find the pH of the solution. So pH plus 2.8 equals 14. That means the pH equals 11.2. And that's the answer to our question, okay? All right, now let's do one more set of calculations. What if we know the pH? What then? How do we do calculations if we know the pH, but we want to find the concentration, okay? Well, the molarity can be found if we know it, the POH or the pH. So the H plus concentration equals 10 raised to the negative pH. The hydroxide ion concentration equals 10 raised to the negative POH. Okay, now let's look at our last examples. All right, so our H plus concentration, 10 to the negative pH, and our OH minus concentration, 10 to the negative POH. Okay, so here's our question. If the pH of a hydrochloric acid solution is 6.10, so the pH equals 6.10, what is the hydrogen ion concentration? So the hydrogen ion concentration equals 10 to the negative 6.10. So in our calculator, if you look at the log button right here, if you do second log, it's 10 to the x. That's what we're going to use. So you're going to type second log, and you get 10 to the caret, negative, not minus, negative 6.10. Enter. So our H plus concentration is 7.9 times 10 to the negative 7. And our units are molarity. Remember, concentrations are molarities. Okay, last one. What is the hydroxide ion concentration for a solution with a pH of 12? So the pH equals 12.00, okay? We want to find the hydroxide ion concentration, which means we need to know the POH. So if the pH is 12, we know the POH has to be 2 so that they add up to 14. So we're going to do 10 raised to the negative 2.00. So in our calculator, second log negative 2.00 equals 0.01. So our hydroxide concentration is 0.01 molar. Okay, there we go. So those are the ways that you can do calculations with pH that will tell you how acidic or basic a solution is.